In this video, we're going to draw some pretty pictures. Or I guess they're pretty pictures of a certain kind. Some people call them math art. We're going to look at fractals. And fractals are images where the image itself has a recursive structure. The fractals we're going to do are quite simple, and so they're not going to be too elaborate or too gorgeous. But if you do a Google search, you can find a bunch of other fractals, and after you work on these, you can try some more elaborate ones of your own. I'm in Fractals starter.racket. The problem that I'm given here is to design a function that consumes a number and produces a Sierpinski triangle of that size. And it says that the function should use generative recursion. And it talks a little bit about how to draw a Sierpinski triangle. You start with an equilateral triangle of a given side length, S, and then inside that triangle are three more triangles, and inside each of those are three more triangles, and so on and so on. And in the end, you end up with something that looks like that. So even without knowing quite what generative recursion is yet, I think we can see that this clearly has a recursive structure. You draw a triangle, inside it there's three more, inside each of those there's three more, and eventually you have to stop. So what I'm going to do is I'm going to follow the generative recursion recipe here, and then talk a little bit at the end about why that recipe works the way it does. So the first thing I'm going to do is do just a little bit of domain analysis. Let's see. If this triangle, this outer triangle, has a side length of S, then that means each of these subtriangles have a side length of S over 2. And that's kind of the end of the domain analysis, really. And I just have to keep making them until they get somehow small enough. So let's see. Let's start following the HTDF recipe for generative recursion, which is like the HTDF recipe, but just a little bit different with regard to the template, and it requires an additional step at the end. We're going to consume a number, which is a side length, and we're going to produce an image. And it's just produce a Sierpinski triangle of size S, or of the given size. Let's do a stub. We'll call it stri S, and it's got to produce some image, so we'll do that familiar blank image that we've done before. Square, 0, solid, white. Now let's do some check expecs. Now, we don't have the recipe for generative recursion mastered yet, but I can tell you right away that one element of it is to do the base case test first. That's going to be in common with the kinds of recursion functions we've already been designing. So what's the base case in a function like this? Well, the base case in this function is that we're asked to produce a triangle that's so small that we're not going to recurse anymore. We've gotten to the smallest side triangle that we're going to make. And I don't know what that is, but clearly that's going to be kind of an interesting number. So, I'm going to give it a name as a constant. I'll call it cutoff, and I don't know, we'll just say 2. 2 seems pretty small. 2 might end up not being right in the sense that it won't look quite right, but since it's a constant, we'll be good to go. So what that means is that if I'm asked to draw a Sierpinski triangle of that size, of the cutoff size, then there won't be any recursion involved at all. I'll just produce a triangle of the cutoff size that is of outline form and is red. And here I'm going to use a trick that I haven't shown you in a while, which is when I'm doing check expecs for graphical things, and I kind of want to make sure my check expecs are right in the sense that the images actually are looking the way I want them to look, a great thing to do at this point is to run it, and the test will fail, but I can actually kind of see what the test was supposed to be. And of course that's very, very hard to see, but you know, there is a triangle there. Let's do another one. Our domain analysis says that the next biggest size of triangle in some sense is cutoff times 2. Of course, it could be not exactly a multiple of cutoff, but just to make my check expect simple, let's do that case. Let's say check expect Sierpinski triangle of times cutoff 2. And what's that going to be? That's going to be a big triangle of that size with 3 little triangles in it. So there's going to be some kind of, we're going to take that triangle, the big one, and we're going to put 3 little triangles in it. So now let's make the 3 little triangles. Well, each of the 3 little triangles is the same, so let me just make one of them using local. I'll avoid redundant computation here. And there's recursion going on here, so this is a good place to avoid redundant computation. I'll say, let's define something which I'll just call sub for the sub triangle. And then what's this going to be? Well, this is just a Sierpinski triangle of size cutoff. Because if I take times cutoff 2 and divide it by 2, that's cutoff. And I know that a Sierpinski triangle of size cutoff is just a triangle, so this is really going to be just this thing here. And now I've got one of them, and I need to arrange the 3 of them. There's kind of 2 on the bottom and 1 on the top. And I could do that this way by saying above the one on the top, and then beside. So this is the bottom row. That's the bottom row, and that's the top row. And if I want to be silly, I could do that, just to accentuate the way it's going to be. That's kind of what a Sierpinski triangle of size times 2 cutoff is supposed to be. Let's run that and see what it looks like. And here we're starting kind of to be able to see it sort of maybe a little bit. You know what I could do? Great thing about having done this as a cutoff, and great thing about having used cutoff in all my check expects, I'll just temporarily make this 20, which is of course going to be much too big for real good-looking Sierpinski triangles, but it'll help me see what my tests are doing. Oh yeah, that looks like a base case, and that looks like a case that's kind of a little bit bigger than a base case. That's looking pretty good. Let me go ahead and make this 2 again. Now I've got the examples. Let's try to code this thing up. Well, what I'm going to do now is get the template for generative recursion. And where I'm going to get the template for generative recursion is I'm going to go to the course website. So I go over to the course website, I go to the design recipes page, and I follow the generative recursion link. And here's the template for generative recursion. I'm just going to copy it and bring it back over to Dr. Racket. Now I paste in the template. This, of course, is the stub. At this point in the course, we don't leave stubs around, but I'm leaving this stub around just because this is the first time we've done generative recursion. This is the template. I'll make 2 copies of it just so we can talk about it. So this is the template. And now let me get going. I've got to rename the template because the function that I want to design is called stry. So I rename the template. I rename its recursive call. And I've been using s for this parameter because it's the side length. So I'm going to go ahead and do that everywhere within this function as well. And now I've got this template. I've got some check expecs. What does this template mean? Well, the way to read this template is this question, if trivial question mark s. Another way to read that question is it's the same thing as saying, are we in the base case? The reason we call it trivial in this template is this is the problem that's so simple that we're not going to have to do any recursion. So when is a Sierpinski triangle so simple that we won't have to do any recursion? Well, it's when the size reaches cutoff. That's sort of what we decided, is cutoff was the smallest one we were going to do. So I'm going to change trivial here to be less than or equal to s to cutoff. I could have made it less than, that's just a detail in how we do this particular function, but I'm saying less than or equal s to cutoff. And now trivial answer in the template is telling me, hey, what you need to fill in here is what you're going to do if there's not going to be any more recursion. Well, I know what I'm going to do if there's not any more recursion. I'm just going to make a triangle of that size. Okay? I'm just going to say triangle S outline red. Okay? That's the trivial answer. So the trivial question is, we've reached the trivial case if s is less than or equal to cutoff, and in that case we make a triangle of size s. Notice I'm making a triangle of size s here. I'm not making a triangle of size cutoff. And the reason I'm doing that is this less than or equal to means that s might be smaller than cutoff. Okay? It's just at least as small as cutoff. So that's why this is an s here rather than cutoff. So then what do I do in the recursive case? Well, it's kind of right here. Okay? I'm going to overlay a triangle of the current size that's outline and red with what? Well, here is the recursion in the template, so I'm going to build around that. And what my example tells me is only do the recursion once, don't do it 3 times. So I'll say local, define, sub. I'm just getting a name for the result of the recursion. There's the recursion, and now what's this next problem thing? Well, next problem is just the piece of the template that tells me, hey, you better not make the recursive call b with s. If you make the recursive call b with s, we've got a problem because this is going to happen forever. You've got to somehow reduce s. And in this case, the way we reduce s, we make a smaller triangle. And each time we make a triangle that's half as big. That's what came from our domain analysis. So we make that triangle. I'm getting this from the examples. And then what do? Well, we do the thing that is in our check expecs. We do above, beside. Let's try it. Hey, the test pass. Let's try a bigger one. What I'll do is I'll make the interactions area bigger by doing a command D, and I'll say stri of 100, and that's a bigger one. Let's see, stri of 200 is even bigger. There you go. You could make them even bigger. Command D to get me back to the code. You can see the problem I'm about to give you, but let me talk about this for just a second. Look, what did we do? We were asked to draw an image that looked like that. We did a little domain analysis. We realized, oh, first you make a triangle, and then you make 3 triangles that are each half as big, and then inside each of those you do it again and again and again until the triangle gets too small. That's cutoff. Then we followed HTDF, good old-fashioned HTDF, pretty much. We did a signature, we did a purpose, we did some examples, we did a stub to support the examples. Then there was one difference here, which we used this new template, this template for generative recursion. And in this template, there were 3 key pieces we had to fill in. The trivial predicate, which meant, hey, we've reached the end of the recursion. The trivial answer, which is what we do at the end of the recursion. In the terminology we used for structural recursion, this was the base case test and this was the base case result. And then we did the non-base case, where we do something with the current value d, and we call ourselves recursively with some next problem, and that's how this ended up looking. It ended up looking just like this. So that's kind of neat. That's kind of fun. What I want you to do now is to do the second problem in this starter file, which is to design a function to produce a Sierpinski carpet of size S. And here's an example of a large Sierpinski carpet. And let me just observe one thing for you that will help. The idea is you make a square, and inside of that square you put 8 copies of a recursive call. Those sit all around the edge, 1, 2, 3, 4, 5, 6, 7, 8. And then right in the middle you just put a blank square of that size. So it's almost the same structure as the triangle. The key insight you need is it's going to be 8 copies of the recursive call to S carpet and a blank square in the middle. Why don't you do that, and then we'll talk when you're done. What I'm going to do now is just quickly go through the design of the S carpet function. Let's see, we consume a number, we produce an image. Now let's see. We start with the base case, or because it's a generative recursion function, perhaps I should say the trivial case, which is that we're making a very small carpet. I'll just use the same cutoff constant as before. Maybe I could have done a different one, but I'll just use the same one. If we've reached that size, then the result is just a square of that size. That's an outline and red. I could also perhaps have made a constant for the color. I didn't do that. Now let's do one that's a bit bigger. Now it doesn't have to be times cutoff 3. I'm just making it times cutoff 3 to keep the math simple. Because of course each of the inner squares is 1/3 the side length of the outer square. So that keeps it a bit simpler for me. If I'm doing that carpet, then let's see, it's an overlay. It's an overlay of a square of that full size. With what? With, well, I need some inner squares, and I'm going to need the same square repeated times. So I'll do that local thing again. I'll call the one that's actually a carpet, I'll call that one sub. And what is that one going to be in this case? Well, it's going to be a carpet of size cutoff, because times cutoff 3 divided by 3 is cutoff. So that's a square of size cutoff, outline, and red. Remember, we're doing the case that's just one bigger. There's just going to be one recursion here. And we also need that blank one in the middle. That's just doesn't have any color to it. That's just a square of size cutoff, but it's, I guess it doesn't have to be solid. The key thing is it has to be white. So now I've got those two. I've got the outer square. I've got the makings of the 9 inner squares. Now I just have to put the 9 inner squares together. Above, beside, sub, 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 beside, sub, blank, sub. Now you see why I used a 3-letter name for blank, right? There's a method to my madness. Beside, blank, blank, blank. That's all of that. Let's run it to see if it's well formed. It is. I can't really see it. Let's do that same trick I did before of temporarily making cutoff much bigger. Running it again, looking at my failing tests, but seeing if the expected values look, that doesn't look very good at all. What happened there? That's not what I wanted. Oh, I put nothing but blank on the bottom row. Silly me. The bottom row has to be sub, sub, sub. Let's see what they look like now. Oh yeah, that looks much better. It's not the full carpet because it's just one level of recursion, but it's a good start. Okay, now I go get the template for generative recursion. There it is. I copy it. I bring it over here. I paste it in. I comment out the stub. I rename the template function. I rename the recursive call. And I like the parameter s for this because it's the side length, so I got to fix all of those. And now I've got to decide some of these other things. Let's see, what is the trivial case? What's the case where there's no more recursion? Or in our old terminology, what's the base case? Well, that's the same as it was for the triangle. It's just less than or equal to s to the cutoff. What's the trivial answer? Well, the trivial answer is we just make a square of this size. And what's the non-trivial answer? Well, we're going to overlay a square of this size with what? Well, we're going to do this local thing so that we don't make the recursive call 8 times. There's the recursive call from the template, but we have to decide what next problem is. Well, next problem is s divided by 3, because each inner square is 1/3 the side length. We also need blank. And it's above, let me try to get it right this time, beside, sub, 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 beside, sub, blank, sub, beside, sub, sub, sub. Run that, test pass, and let's try a big one. That doesn't look quite right. Why doesn't it look that right? It doesn't look rich enough. Oh, I know what's wrong. Forgot to change cutoff back to 2. So there's not many levels of recursion. Let's try it again. This is taking longer. Yeah, that looks a lot better. So there you go. That's my version of the Sierpinski triangle and the Sierpinski carpet. If your version of the carpet came up significantly different than that, or even different, be sure to compare my version to your version and be sure that your version really only differs in details. Your version really still has to have this same recursive structure based on this template. And then in the next video, we'll talk about the last piece of the recipe for generative recursion.